cartoon character, and that's because sound travels about 3 times faster in helium than it does in air. So it changes the natural resonant frequencies of the cavities in my head, and it makes me sound kind of funny. But as I continue to breathe, little by little, the helium is replaced by air, and I begin to sound normal again. So there are many things we can illustrate with gases, but I've showed you some demonstrations that involve the physics of motion, and some demonstrations that involve the physics of heat, in particular things that are quite cold. And we've shown you some things that make a lot of sound, and sound is another area of physics. And I want to show you an example of what sound is. Sound is actually a form of wave. Now when you hear a wave, you probably think of waves on the water. Out on the Nile, there are nice waves that you can go and watch. But there are many forms of waves. In fact, radio waves you've probably heard of, or even light is a form of wave. But sound is also a form of wave. So we're going to show you here a wave on a string. And so this string is a little like the string on your guitar or on a violin. On one end we have a weight just to put it under tension. On the other end we have a little vibrator that goes up and down very rapidly, about 50 times every second. And that's making it vibrate. And if we adjust it just right, you can see it vibrates so that there is a large vibration here and here and here, and very little vibration here. These are called nodes, and these are called antinodes. Now I can demonstrate that a little better using the strobe light and adjusting the frequency of the strobe light so it is synchronized with the frequency of the vibrating string. And you can see it makes the string appear to come to rest. And that's because we're illuminating it at the same frequency that it's vibrating. But you can be assured that the string is vibrating very, very rapidly. Now, that's a form of wave that we call a transverse wave. That's not what a sound wave, or sorry, that's transverse wave. Sound is not that kind of wave. It's what we call a longitudinal wave. When I'm talking and you're listening, the air between my lips and your ears, or actually between the speakers and your ears, is vibrating, but it's not vibrating up and down like that. It's vibrating back and forth. And that's called a longitudinal or compressional wave. Now I have one other sound demonstration here. Here I have a little gadget that makes a sound. I'm going to turn it on and see if you can hear the sound. It's not very loud. Can you hear that? Except I'm going to have to turn my microphone off for a minute. Now I hope you noticed a peculiar sound. It went woo, woo, woo. When it was coming toward you, it was making a high pitch. When it was going away from you, it was making a low pitch. And you may wonder why I turned my microphone off, and that's because I was right in the middle. It wasn't coming toward me or away from me, and so the sound that I was hearing, and that would be picked up by my microphone, would not hear the sound that you heard at all. And that's something called the Doppler effect. And you're probably all familiar with it. If you go out on the highway sometime when cars are coming by, I notice they honk their horns a lot here in Egypt, and if a car is coming by honking its horn, you know what it sounds like. It sounds like, "Meow." You've heard that, right? So when it's coming toward you, it has a high pitch. When it's going away from you, it has a low pitch. And that's the Doppler effect that you're all familiar with. And that's how the police measure how fast your car is going, not using sound waves, but using radar, which is another form of wave, an electromagnetic wave, but it also exhibits the Doppler effect. Okay, so there are many things that have to do with the physics of sound, but I want to tell you another kind of wave, and that has to do with electricity. Electricity can also form waves. We call them electromagnetic waves. And there are many ways to make electromagnetic waves, and we have here one little gadget called a Tesla coil. And if Ahmed would plug it in back there and turn it on, It makes a very high voltage, high frequency electric voltage. And it produces about 50,000 volts, and it's basically a transformer. It has one coil of wire that is at low voltage, and then there's another coil with many, many turns on it that steps the voltage up to a very high value. Now, to convince you it's really doing something, I'm just going to take this fluorescent light, very similar to one that perhaps you have at home, or at school, or at work. And you see, I don't even have to touch it. I just have to bring it near, and you see how it lights up. And that's because there is electricity in the air. These radio waves produced by this are absorbed here, and the electric currents pass through the air, they pass through this tube, they pass through my body, right down to the floor and back to the ground. So I'm part of the electric circuit that is formed when we do this. Now here I have another light bulb, a little more like the kind maybe you're familiar with, an incandescent bulb, except this one has the coating removed, the white coating you normally see. And I can touch this to the terminal of the Tesla coil, and you see the sparks that form inside. And those are a little like bolts of lightning, little tiny bolts of lightning. Now I should caution you, of course, electricity is potentially very dangerous. And this is safe, first of all, because the current that it can supply, the number of electrons that it pushes through your body is very, very small, and furthermore, the frequency is very high. It would certainly not be safe to do this with the kind of voltage that comes out of the wall socket you have at home. This is at a frequency of maybe 100,000 cycles per second, whereas what comes out of the wall socket is a mere 50 cycles per second. So it's safe because of the very high frequency and because of the very low current. Now that's an alternating current. I have over here a device that will make a very large direct current, or a DC voltage, and it's a device that we call a Van de Graaff generator. And it's a large dome, and below is a rubber belt that goes around, and at the bottom the belt collects electric charge, and it carries it up to this dome where the dome begins to acquire electrons. And when I turn it on, you will see these strips of paper begin to rise up. Now sometimes we have a volunteer come down with the right kind of hair, and we make their hair stand up, but we won't do that today, but just pretend this is someone's hair, and you may wonder why that happens. And it happens because all of those little strips of paper are negatively charged. And charges of a like sign, two negative charges, repel one another. And so they try to get as far apart as they can. And so they stand up like that. Now we have over here another gadget that consists of two plates, one that is on a spring that can go up and down, and the other that's fixed. And what we're going to do is connect the upper spring here to the ground, and the lower plate we're going to connect to the terminal of the Van de Graaff generator. And this again produces a voltage of maybe 50,000 volts. And what we're going to do is charge up this lower plate with electrons, accumulate lots and lots of electrons on it. That's going to pull, that's going to cause the electrons in the upper plate to move away, and they will move up or through the spring and down to the earth, and that will leave the two plates with opposite charges, negative on the bottom, positive on the top, and you would expect them to attract. So let's try it. We turn it on, and you will see they begin to attract, but of course the spring pulls it up, but then it comes back down again, and as it goes up and down, it oscillates, and you see eventually the plates touch. When they touch, they discharge. All of the electric charge goes away, and when that happens, the plates are no longer attracted and the spring pulls them up. And you can tell that they're discharging if you look at the paper strips on the Van de Graaff generator. When it discharges, they fall back down. When it charges up, they come up again. So we have made a peculiar kind of motor that goes up and down using pure electricity. Now, closely related to electricity is another principle of physics that has to do with magnetism. Some people confuse magnetism with electricity, but they are two different forces, but they are closely related. In fact, one way to make a large magnetic field is with an electric current. If you take a bunch of wire and wrap it into a coil, pass an electric current through it, you can make a magnet. And here we have an example of that. Here we have several hundred turns of copper wire, and I'm going to energize it and make it into a magnet. So when I do that, there's a north pole on the top here, there's a south pole on the bottom, it momentarily becomes magnetized. Now I have here a little ring made out of aluminum. It's about the size to go on my finger. Actually, it would make a nice ring, I guess. Aluminum is not normally a magnetic material. It's not normally attracted to a magnet. However, this is an alternating current. And so when I lower this down over the magnetic field will rapidly change. At some instant of time, it will go up. At other instants, it will go down. It will oscillate up and down, and that causes an electric current to flow around the outside of the ring. That makes this momentarily magnetic, because remember, an electric current makes a magnet. So if we induce a current in this will become a magnet. It will then be repelled by this other magnet, and let's see what happens. That went pretty fast. Let's do that again. Now, would you like to see it go higher? Everybody likes that, don't they? Well, actually, there is a way to do that. What I'm going to do is take this little ring and lower it down into the liquid nitrogen. Now, most substances become better conductors of electricity when they're cooled down. In fact, aluminum becomes about a 7 times better conductor of electricity when it's at the temperature of liquid nitrogen than it is when it's at the temperature of the room. And so, one would expect a larger electric current to flow in it, and therefore it would be a stronger magnet. So, we have to wait for it to cool down, and I know that's happened when the boiling stops, because as long as it's boiling, I know that the ring is hotter than the liquid nitrogen, and it's causing it to boil. But right now it has stopped boiling, and now I don't dare put my fingers in there, so I'm going to take these tongs and reach in and get the ring out and lower it down over the magnet again and try it again. Once more. Okay, so that illustrates many principles of physics. The way you make magnetic fields with electric currents, the way magnets repel one another, the way you induce a current in one conductor from a nearby electric current, and the way that the electrical conductivity changes as a function of temperature. Okay. So the last area of physics I want to talk to you about has to do with the physics of light. Now, you may think light has nothing to do with anything else I've talked about, but light is a form of wave, like sound, and it also involves electricity and magnetism. Light is a form of electromagnetic wave. Inside of a light wave, the light coming from the lights overhead, there are electric fields and there are magnetic fields, and they're oscillating very, very rapidly as the light propagates toward us. Now, there are a number of interesting things we can do, and one thing I would like to show you involves this beaker of water, the same beaker I used before to demonstrate inertia. I'm going to put it on this overhead projector and make a white spot of light there, where the light comes up through the bottom of the beaker of water and is projected on the screen. Now, what I'm going to do is take a little eyedropper and put a little bit of milk in the water. So, let's squirt some milk in the water, then I'm going to stir it, and watch the dot on the wall. Now, you don't see a whole lot that's happened yet. Let me put another dropper full of milk in there, stir it again. Can you see the spot on the screen beginning to look a little bit reddish? And this illustrates what happens when the sun sets. Of course, when the sun sets, you know, it's often a beautiful red color. Let's do one more. And it's for very much the same reason as what you see here. So now it's getting noticeably red. Let's do one more. So the water with the milk is acting like the atmosphere, the air and the earth. And the overhead projector is like the sun. So what you're seeing is analogous to the sunlight passing through the atmosphere of the earth, being looked at with your eyes. Now, at the same time, you see the red setting sun. If you look up in the sky here at the light that is coming out of the water right here, you see it has a little bit of a bluish tint. Let's do just a little bit more. Try to make it red. If we go too far, it'll be too dark for you to see. And that's because we have mostly scattered out the red light. White light, of course, is made up of all the colors of the rainbow. And if we scatter out the blue light, which is what's happening here, you're seeing blue here, we're left with light that is deficient in blue. If you take white light and remove the blue, what you're left with is something that is somewhat reddish. And so that's what we have here, a kind of a red light. So this is a principle of physics that involves what we call Rayleigh scattering. And it is why the sky is blue when you look up in the daytime, and it is why the setting sun is red. And so that illustrates several principles that involve the physics of light. Actually, let me leave this here because I now want to turn on another source of light that's rather different. This light comes from what we call a laser. And a laser makes a very intense, monochromatic, polarized form of light. And you've probably seen that. Can you see the dot on the wall over there as I move it around? I'm going to just set the laser here so it doesn't move. Let's see if I can set it up. Let me set it on something. Prop it up. Yeah, very good. Well, I wanted to aim it up a little bit.
Can you do it?
Okay, we can try that. No. Yeah, okay. It's a little bit tipsy. Can we just... let's try like this. Okay. Now, you notice, you see the laser beam on the wall there, but you don't see it in the room here. And that's because the air is quite clean in here. If the air had dust particles in it, as sometimes happens, especially in the city where there's a lot of pollution, you'd be able to actually see the laser beam go across here, but you can see where it touches my hand. Now, what I want to illustrate to you is a phenomenon that you've all encountered. Have you gone out on a clear night when you can see the stars, and have you noticed that the stars appear to twinkle? And you may wonder why that is. And I can actually show you that using a source of flame. Here we have a blowtorch that makes flame, and I'm going to turn it on and make a flame. And I'm going to bring this over near the laser beam. Now you notice right now the little dot on the wall is quite steady, but if I bring this flame over near the laser beam, you see it begin to dance around. And that's what happens when you see a twinkling star. Now you may say, well, there's no blowtorch out in the night when I see stars twinkling. But what's happening here is that we're heating the air. And when the air heats, hot air, as you may know, has less density than cold air. And as the hot air rises off the heat of the flame, it rises just like a balloon rises because it's less dense than air if it's filled with helium. But here we have air that is rising purely because it's warm, much like in a hot air balloon. and that forms turbulence. And if there were a little bit of smoke in the room, you've probably seen that off of the tip of someone's cigarette where the air becomes highly turbulent. And so that turbulence causes, light normally travels in a straight line, you think, but when it goes through a region of air where the density of the air changes, it deflects the light ever so slightly. So what's happening here is as the laser beam is moving through the turbulent air, where the little bits of low density air is moving around, you see the dot on the wall moves around. Now, out in the real atmosphere, as you're looking up, you're seeing through lots and lots of atmosphere. Not just a little region here that is heated, but the whole thickness of the atmosphere. So even though the temperature differences may be rather small out in the night sky, the atmosphere is thick enough that it adds up to a significant deflection of the light that you get from the stars, and they don't twinkle. It causes them to twinkle. Now, you may have heard that the planets don't twinkle. Well, they would, except that planets are larger, and so when they move around, you don't notice it so much. And so, for the same reason, the moon doesn't twinkle. It's very large, and when it moves a tiny little bit, that's completely invisible to you. But when a very tiny dot of a star moves around, you can see it quite easily. Well, that brings me to the end, and I want to just point out to you that all of the things you've seen today are not magic. They all are a result of the laws of physics. Now, you know about laws. Every country has laws, and the laws may be different from one country to another, and they may change from one year to the next. But the laws of physics never change. They have been the same from the 14 billion years ago at the Big Bang, and they will be the same for as far into the future as we want to go. And furthermore, human laws, you can break them. They put you in jail when you do that, or even worse. But the laws of physics you can never break. And so it's a very good thing to learn physics, because you're learning something that is eternal and unchanging, not like so many other things that you learn in the world that will be different in just a few years, perhaps. The laws of physics are very fundamental and very important in understanding the world around us. So I'd like to thank you for attending The Wonders of Physics.